Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start a new subject, that is power electronics. So power electronics is considered a very important subject, and in the modern era, right, from electrical domain, it is the one of the most important subject in which research is happening. So power system analysis and electrical machines, in those subjects the research work, right, has been saturated, but power electronics has electronics written in it. So hence we know this era is of the semiconductors, and power electronics also has a huge role to play. So this is a very important subject if you are from electrical domain, and in general in your college also, in other places, right, in interviews, electrical interviews also, this may be asked. Okay, and in gate this has very high weightage. So today we'll start the first chapter, that is the power semiconductor devices. We'll understand to use power electronics, right, what devices we need. With the help of those devices, we'll be able to accomplish our task. What are the tasks? I will tell you. Okay, so the most important device in the power electronics subject is the silicon control rectifier, that is a SCR. Okay, obviously this is the most important device, and we'll study about this in a brief manner, in full detailed manner. Okay, so obviously there are more devices, we'll study about those also. So let's basically divide our power electronics into mainly 4 sections. So first section is the power semiconductor devices, which we'll start today. In that, right, there are many things. Basically first we'll understand what are switches, okay, and why do we need switches, we'll also understand that, and what are the classification of switches. These are the classifications, and inside this classification, right, there are multiple more classifications. We'll understand all of this. We'll understand bit about constructions, we'll understand their working as well. Next is the phase controlled converters. Basically these are the rectifiers, right, which convert what, AC to DC. Okay, in power electronics mainly we need conversion. Power electronics is a conversion. I will tell you the definition later on. So in that, right, it can be single phase controlled rectifiers, 3-phase control rectifier, and few extra problems arise when you implement these rectifiers with power electronics devices. So like problems of source inductance, and obviously we'll understand about dual converter, that is for ESC. We'll see if you cover or not. That is specifically for ESC, that is not for K. Okay, next is the choppers. Choppers is the conversion of DC to DC. Now you might say, why do I need conversion from DC to DC? Because sometimes what may happen is you have a DC voltage of 50 volts, but you want your phone, right, to work in 5 volt DC. So you don't want that much high amount of DC, and you know, right, we don't have a component like transformer which can step down or step up the voltage, because transformer doesn't work in DC. So we need a new device, and that device is chopper. We'll understand about that also. And then inverters. So these 3 are the main topics. Inverters is, we know, in our homes, right, whenever current goes off, your parent, your father or mother says like turn on the inverter or something like that. So what happens basically, inverter basically converts DC to AC. So inverter has a battery, and in battery, right, generally the type of current that flows is DC, but we need AC, right? All our supplies, all of these work in AC. So we have to convert that into AC, then only we will be able to work, you know, on our supplies. So that is what the task of inverter is, and their weightage is written, right? So like these are tentative marks. Obviously they can ask from anything, and anything can happen, but this is the most expected from which they can do. Okay, so basically from the first chapter it can be of 1 marks, or they can ask for 2 marks as well. From the second chapter, this is a very important chapter, they can ask from 3 to 4 marks, and choppers is also very important, 3 to 4 marks, and inverters is 1 to 2 marks. And trust me, the highest weightage is of these 2 chapters, and the most easiest are these 2 chapters. I will teach you in such a manner that you don't have to remember any formulas, because there are hundreds of formulas. Yeah, in phase control rectifier, I do agree, there are hundreds of formulas, and you have to remember few of those for 3 phase, right? But for choppers, right, we can solve in seconds, like with the help of transient. Okay, you can solve in seconds, and overall weightage of the subject is 8 to 12 marks. So in core, right, all 3 subjects are very important. You can't leave out any subject, because they can ask from the 3 subjects with equal weightage, so you can't leave out anything. So this is basically the overview. In choppers there are few types, and in inverters also there are few types. We'll go through them in detailed manner when we go into the subjects. Now let's basically like there are few extra topics, that is basically resonance converter, AC DC drives, SMPS, and AC voltage controller. These are mainly asked in ESC. Sometimes they get asked in gate as well, but these are mainly in ESC. We'll see how much we cover each of these topics, because like these are not that important for gate point of view. Okay, so now let's basically start our lecture 0. So in lecture 0, right, I will introduce you to power electronics. We understand what does power electronics mean, what is the definition of power electronics, and why do we need switches, and what is the difference between ideal and practical switches, and what are different switching losses that can happen, and few numericals on that as well. So like the numericals I will give you few assignment problems, and those we'll solve in the next lecture. Okay, so but before starting, right, I wanted to say that like I will put those like prerequisites, all the prerequisites, right, I will put those here. Like whatever prerequisites you need, basically I will say like there will be one folder just before this. Okay, just before this, that what are the prerequisites. The prerequisites are basically you need to have good knowledge of inductors and capacitors. I will put all the videos in the folder there, all the videos will be present. Inductor and capacitor, then basics of diode construction and basics of diode as well, and MOS physics as well. Okay, MOSFET and MOS physics, that is like not the circuit analysis of MOSFET, just the MOSFET physics part. And the first lecture, all the links will be provided just before this, right, or just before this, all the links and all those things will be provided in the folder just above this. Okay, so let's first start with our power 20. So like you have to watch those prerequisites if you haven't already. If you have, you can proceed, else you first watch those prerequisites, then you can come. Okay, because like I want to go in a flow and I don't want to lose out on the flow, that's why. So what do we mean by power electronics? So power electronics is the application of electronics and circuitry to control the electrical power conversion from one device to another. So it basically like controls the power conversion from one device to another. Okay, so let's say I have a source and there is one power processing circuit. So this is where the power electronics comes into the picture. This section, right? This section is the power electronics part. So I have a source which gives me AC supply, right? I have a source which gives me AC supply, but I want a DC supply. So how do I do that? So with the help of power electronics, I can convert my AC to DC. Let's take an example. Electronics. What is the example? The example is our mobile charger, right? If you observe carefully, in our smartphones there is a battery which is lithium ion, and it takes DC current. But our source, right, this switch, whatever supply we get is AC supply. So obviously I can't give AC to my phone battery. That will just damage my device. So we have chargers. So like let me just show you one charger. There is one charger, right? So this is a charger. So what does this does? This converts AC into DC. So if you observe this, right? Okay, you can't see from here. I will show another charger. So in here, right, few things will be written. So if you just observe it carefully, few things. If I may just focus on it, if it can, yeah, I don't think it can focus. Okay, like you just see charger, few things will be written, right? Like in this it is written that input is 100 to 240 volts, 50 hertz to 60 hertz, and output is 9 volt DC with 1.67 amps current. So like you can observe your phone charger as well, right? You can observe your phone charger as well. You can see all these things are written. So what it does, it basically converts AC to DC, and that is like this is power electronics, right? Obviously semiconductor is involved and power electronics is also involved. So all these things are the work of power electronics students, whoever has studied power electronics. So this circuit in between is a power electronics. What it does, it basically sees the AC, then it converts, like it has a rectifier and transformer, and then it converts and it steps down the voltage and also converts into DC. So this is basically our main target of power electronics. So converting our AC to DC, or our DC to AC, or DC to DC as well. Okay, or AC to AC as well. So like in a controlled manner. So that is the main particular application of power electronics. This acts as an interfacing circuit, and it is also used to regulate and control output. It contains power semiconductor devices. So it is also used to regulate and control the output, as I mentioned, and it contains power semiconductor devices. So we have already semiconductor devices like MOSFET, BJT, diode, but power semiconductor devices are a bit different. Why? Because the name power is written, right? Power, generally what happens in EC, right, in semiconductor domain, we use our devices in low voltage, in low current region, right? But in power, like you see our transformers, we have 11 kV transformers in our substations, in our powers, like in power generation areas, like it is generating power at 11 volts, then is coming to this like substation, then in our homes, right, this is 230 volts. We generally don't apply this much amount of high volt in our small semiconductor devices. But when power comes into the picture, obviously we have to deal with these high voltages, because I want to convert 230 volts into, let's say, some 5 volts 1 amps of current. So from 230 I need to convert it into 5 volts 1 amps of current. So obviously power semiconductor devices have to have higher rating than normal semiconductor devices. So you will notice that once we go into the switches, you will see about the properties. We just make a minute tweak to our normal semiconductor devices. If you have studied MOS physics, if you have studied diode, if you know the construction, we'll make a minute tweak so that it is suitable for higher rated voltages as well, right? So that is the main purpose, just to tweak the construction a bit of the previous devices so that I can make it I can use it for my power electronics application in higher voltages. So we'll see that. So that is basically about what do we mean by power electronics. Next, you can also see power electronics convert control and conditioning the flow of energy or using power electronics switches. Flow of energy or power using power electronics switches. Okay, so it converts, control and conditions the flow of energy or power using the switches. So switches are important. How we will use the switches, I will explain it. Okay, all those things I will explain when we study about each of the subtopics. Okay, each of the chapters. So what are the few power electronics devices? Like this is power diode, BJTs, MOSFET, IGBT, SCR, triac, diac. All this we'll study in this whole chapter. Don't worry. There is always a mismatch between availability of supply and the load demand, as I explained, right? So I have 230 volt AC supply, but I need 5 volt 2 amps of current in my mobile phone to charge. So there is a mismatch. Hence, to cope up with this problem, power electronics is very useful. So like here I've given few examples. What are the examples? Let's say I have an electric lamp which works in a DC, right? 12 volt 2 amps, but my supply is 220 volts 50 hertz. So there is a mismatch, right? There is a mismatch for this. There is a mismatch. Now next is I have a tube light which works in 220 volt 50 hertz AC, but let's say I have a battery. I want to turn on the tube light with the help of a battery. There is again a mismatch, right? This is AC and this is DC. I have a battery that is DC. So again there is a mismatch. Again, let's say I have a 12 volt battery that I want to charge. That I want to charge, but I have a 9 to 48 volt variable DC, right? So how can I get constant 24 volts in the battery, but I have a variable DC? So again, there is a mismatch. I want exactly 24 volts. I don't want this variable thing, but they are providing me variable thing. So there is a mismatch. How can I match this? So I can match this basically with the help of 3 devices. The first one is like this is converting DC into what? Sorry, I have AC and I want to convert to DC. So AC to DC is where the rectifier comes in. Okay, so we'll write here rectifier. It converts AC to DC. Okay, next is this mismatch, right? DC to AC. So supply is 12 volt battery DC to tube, right? AC, right? So basically I am converting DC to AC here, right? Inverter comes into the picture. I have already explained the overview. There I have written which device converts which type of supply, DC to AC. Next is this, right? This is also DC, but this is variable DC. So basically whenever variable DC or something you see, right, DC to DC, that is generally the application of chopper. So we will use chopper, DC to DC. Okay, so all this we'll study in detailed manner bit by bit, right? So first, in the first chapter we'll not study about any of the devices. We'll study which type of switch goes into these devices. That is very important. Then only we can study about this devices as well. Okay, so like what is the difference between power electronics and analog electronics? I have mentioned previously as well. Analog electronics mainly works for low power devices. Power electronics mainly works for high power devices. Electrical people, they are like making power generation substations, all those things. So we work in high voltage, and analog electronics people work in low voltage, ICs and all those things. So what are the few examples? Examples are speed control of DC motor. That is also with the help of power electronics. You can see the block diagram, okay, how it is controlling. If you have studied machines, you will understand how this is controlling the motor, right, speed. Then also HVDC transformer. So in HVDC, right, first we get AC and then we convert it into a DC voltage. Then with the help of DC, we step up the voltage. Then again here, right, we again step down the voltage. So people who have studied power systems, they will understand what does HVDC transmission means, and in that, right, there is an application of power electronics. In here also there is an application of power electronics. I'm just saying the application, right? So don't need to like worry about this. Just I'm giving you a few examples like in real life where we use it in power electronics. So like advantage and disadvantages of power electronics. What is the advantage? Advantage is improves efficiency, improves power factor, significantly reduces weight of the system, increases life expectancy of the system, and fast controlling action. So how does it improve efficiency? Because there is no moving part in power electronics, right? The switches, there is no actually moving part. Okay, so I will write here no moving part. So that's why efficiency increases, and that's why also the life expectancy increases, right? And why is there fast switching action? Yeah. Because fast controlling action, because we are using electronic devices, because electronic devices are very, very fast. Instead of if you would have used a mechanical or physical device, that would have been difficult. But electrical devices are very fast. That's why, and also this doesn't have any moving parts. That's why the controlling action is always fast. And how does it improve power factor? How does it like reduce weight? We are using like semiconductor devices. They are very lightweight, right? That's why. Like all these disadvantages are for basically if we would have used mechanical devices. So this is comparison to mechanical devices. Why we don't use mechanical devices? Okay, how does it improve power factor? I'll say later on. Okay, so what are the disadvantages? Introduces switching problems in the system. So these devices that we use, right, SCR, BJT, MOSFET, IGBT, these devices has few problems as well. We can turn on and off, but they introduce, while turning on and off, they introduce few switching problems. Those are present. Okay, those were not present for mechanical devices. Introduces harmonic. So if you know a bit about harmonics, right, basically harmonics are basically components which you don't want, are the like undesirable quantities. So I will explain about harmonics just in the next slide, and also we'll study this in more detailed manner in machines, okay, and in power systems as well. So harmonics are the undesirable things that are present in the waveform, supply waveform, that we don't want, or present in the input waveform that we don't want. Okay, now requires additional protection due to heat loss. So obviously we are like in power electronic devices, right, they are turned on and on, let's say 1000 times every second, or every 5 seconds, or every 10 seconds, 1000 times it is turning on and on. And during turning on and on, right, although this is not a mechanical switch, what is happening? The flow of electrons is reversing. It is going and reversing, like it is getting suddenly stopped and then reversing. So when it is getting suddenly stopped, right, it still has some inertia with it, and due to that obviously there will be some heat loss, and that will be the loss, switching loss, due to which we get, like you will study about switching loss also, and that will be converted into heat loss. Basically the switching loss will be converted into heat loss, and like these are the disadvantages. But obviously we can control all this. Okay, advantages are far superior than disadvantages, obviously that's why we use this. Okay, now why harmonics are undesirable? Why harmonics are undesirable? Like I've given few points. Like first of all, you need to study what are harmonics, so that we'll study in machines. So if you have studied machines for me, you will understand. Else don't worry, I think if you have already studied machines, you will also understand that. Okay, degradation in the quality of electric power supply. So I have a sinusoidal, pure AC sinusoidal waveform, but if there are harmonics present, it won't be pure sinusoidal, it will be something like this. Okay, something like this. Now will you like it? Will you like a noise in your waveform? No, right? You don't want. You want, like, if you want a pure sinusoid waveform, you will want a pure sinusoid waveform. You don't want a waveform like this. Okay, we don't want a waveform like this. So obviously that's a drawback, and that will cause your devices to not work properly. Your device expects pure sinusoid waveform, or your device expects pure DC waveform. If you're getting DC with few ripples, right, few ripples, that is also not good for your device. It is harmful, it can damage the device. So obviously we want either pure DC or pure AC. We don't want harmonics, but basically the undesirable quantities. It also increases the loss within a distribution system. All this we will understand in power system. Just the few few things that are not good about harmonics. like overload in the neutral conductor, basically all the harmonic component that will flow through the neutral conductor itself. If the like if our neutral is balanced, right, if our system is balanced, our neutral current will be 0 and there will be no current flowing through it. But if the system is unbalanced, neutral current won't be 0. Okay. Okay, but if it is unbalanced, neutral current won't be 0. Then vibrations and premature aging of generator, motors and transformers. We'll understand this when we will study about machines. Increase in noise levels, distortion in the power supply, interference in the telephone communication lines, and obviously increase in machine core loss. All these are disadvantages of harmonics, and we don't want. Obviously, this is a very big problem, and we'll have to solve this. How will you solve this? We'll see that also. Okay, so like I've given you the proper reasoning why harmonics are undesirable. Now let's understand, like in most of the devices, right, you will see silicon being used. Why do we use silicon? Why don't we use any other quantity like germanium or like carbon also we can use? Why don't we use up until now? Like there has been like research is ongoing, still research is ongoing, so we can use some other component as well, but for now we are using silicon. Why are we using silicon? Why do we love silicon so much? So silicon is preferred over germanium because its atomic number is 32, whereas silicon's atomic number is 14, and that also helps. Okay, that also helps. How? I will say the energy band gap, all those things, due to all those things. The valency of electrons in both atoms is same, but they are in different cells. In silicon, the valence electron are in third cell, whereas in germanium, the valence electron are in fourth cell, which means they are further away from the nucleus. So valence electrons experience less force of attraction. Silicon has more force of attraction of their valence electrons, but germanium has less force of attraction. That is point 1. Okay, due to that we require less energy to flow current. That is also a reason. They could be then easily escape the outermost cell and get free. Okay, this also means that the ionization potential of germanium is lesser than that of silicon, but silicon atoms are more stable than germanium atoms at high temperature. Also, silicon is abundant in nature; they are less expensive than germanium. So all these are reasons why we chose silicon. Look, I will not go too much into the details, but these are the few details. If someone who have studied chemistry and all those things, they will understand. But don't worry, all these are not that important. Just to the people who are interested, why do we use silicon so much? Now these are the comparison between silicon and germanium, right? So you can see, just hold on a second. Yeah, sorry for the interruption. So as I was telling that, let's compare the silicon and germanium. So you can observe that silicon has a thermal limit of only 100, sorry, germanium has a thermal limit of only 100 degrees, while silicon has 200 degrees. It has low voltage rating, this has high voltage rating. It has low current rating, it has high current rating. Power rating is obvious low because the current rating and voltage rating is low. So but for this both are high, so it can be high. Availability is medium, this is high. So that's why we use germanium and not use silicon. Germanium is also a useful component, okay, parameter, like what do you say, atom, but we use silicon, okay, for our semiconductor devices. Like another reason is energy band gap. You can observe, right, like this, due to this only all these things are high and low. Okay, so you can observe, like if you have studied a bit of physics, right, like semiconductor physics, you will know that in like our silicon, right, the band gap is 1.1 electron volt, and in germanium the band gap is 0.72. so this is higher energy band gap. So from valence band to conduction band we need higher energy. Okay, so that's why it doesn't go that easily to the conduction band. And what is the advantage of this? The advantage of this, like previously if I said, I may have said it other way around. Okay, just like ignore that. Now understand this. If the band gap of silicon is higher than germanium, what happens? I will need more energy to place a electron from valence band to conduction band. I will need more energy. Now if I need more energy, that means what? My energy band gap of silicon is greater than energy band gap of germanium. Now if it is greater, what does it mean? Basically the conductivity of silicon will be lower. Conductivity of silicon will be lower than conductivity of germanium. Why? Because I am like I need more energy to place this electrons into conduction band, right? Okay, this like pass through this energy band gap. So you might say, sir, then conductivity is low, so why we'll use it? We'll use it because we need it. We don't always want to flow current, right? We want to turn off the current as well, totally. Okay, and why I will explain later on. But we like, what is the point then? If you always want to only flow the current, what is the point? We won't be able to convert. We won't be able to convert the type of the single type of the power, right? So that's why we don't always want to flow current. And if the conductivity is more, right, there will be more leakage current in germanium, more leakage current, because with just lower energy, one electron can flow from valence band to conduction band. So there will be more leakage current due to it. Okay, so even if I give this silicon, right, I give this 0.72 electron volts of energy, its electrons won't move. But if I give this germanium, just hold on, if I give this germanium 0.8 of electron volts, electrons will go from valence band to conduction band. So we don't always want it, right? We want to give, like, we want to flow current, but by giving some control, and then it can flow. Okay, so basically it has more leakage current. Germanium has more leakage current. So this is also another reason. Why am I telling all this? Whatever I'm saying, right, theoretical things, these are important, because in ESC they can ask. Okay, in gate also sometimes they ask few things. So obviously I will not go too much deep into theory. Obviously we'll do numericals and all those things. We'll do the theory, whatever is required, that I will do. Else if you want to learn more things, right, I will like in the intro video I may have said about books and all those things from where I have studied and all those things, so you can follow those books. If you want to go more deeper into power electronics, whatever I will say, don't worry, that will be enough for gate and ESC. Okay, so like you don't have to see any book or anything, right? Whatever I will teach, that will be enough for gate and ESC. But if you want to dive more deeper into the things, obviously you can follow those books, which I have said in the lecture 0 or the introduction of power electronics roadmap video. Okay, so like now let's come to switches. We have understood why do you use silicon and all those things. Let's come to switches. Okay, let's understand what are different types of switches. So like first of all, what is a mechanical switch? Mechanical switch, if you know, like in your home, right, this is a mechanical switch, right? If you see, this is a mechanical switch. So this can either turn on and off, and like if I push this will be on, and if I like press it up, this will be off. So like this is known as pole and throw, or name you don't have to care about. Mainly what you have to care about is there is a mechanical contact, and you need, like, a person is needed to operate this, right? This won't turn on and off automatically. A person is needed. Okay, if a person is needed, the speed of turning on and off is limited, right? I can only like turn on and off so much. Okay, like my fingers are there, and you know, people, they are not robots, so we have limited amount of power and energy. So switching frequency is of mechanical switches are very low, because this has to be operated by a person. Okay, and a person doesn't have the machine like hands, whether it can turn on off very fast. Now time taken to turn on or off of the switch is also very large, because I will take some time to turn it on then off, right? Press it on and off, so that is also very large. Time taken to turn on and off the switch is very large, as it is operated by human. Generally mechanical switches are designed with the help of aluminum or copper conductor. So this is basically a mechanical switch, and this is the the parameters are current, voltage, and power through the switch. What is the power? We understand about power of the switch as well. Okay, now we don't use these switches. Okay, but let's understand the characteristics of a switch. What does a switch does? Let's first understand that then we'll understand about electrical switches in the lecture, like two lectures after this, right? First we'll understand what is a characteristics of a switch. So if we have an ideal switch, right? If you have an ideal switch, mechanical switch, then if it is on, right? If it is on, it should allow all the current to flow. It should allow all the current to flow. So if it allows all the current to flow, what will be the drop across the switch? It will be basically like a wire, right? It will be basically like a wire, and the drop across the switch will be 0, because drop across the wire is also 0. So V switch is the drop across the switch, which is VSW. VSW equals to I switch can range between minus infinity to infinity, right? Like max value can be anything, and mean value can also be anything, because it can flow any value of current. Okay, any value of current it can flow if the switch is closed, if an ideal switch is closed. Okay, now how much power can it dissipate? Obviously, for an ideal switch, right, the power or the conduction, like power dissipated during conduction, it should be 0, because my V switch is exactly equals to 0. V switch is exactly equals to 0. There is no drop across the switch, so obviously it is V switch times I switch, it will be 0. Okay, now what is another point? Another point is how much time does it take for this switch to turn on. Basically, for an ideal switch, it should be instantly. It should be instant, right? Instantly. So time for this switch to turn on is 0 seconds, right? It should turn on instantly. There should not be any inertia or any slowness. Okay, now what are the off state parameters? So again, during off state, right, what do we care about? We care, right, during the switches, when the switch is open, there should be no current flow, so I switch should be 0. I switch should be 0, and V switch should be like it can block any amount of voltage, whatever the voltage is, I don't care, right, across the switch, whatever the voltage is, I don't care. If I've opened the switch, it should be able to block any amount of voltage, that is, the range is from minus infinity to plus infinity. Okay, whatever the voltage, I don't care about the voltage across the switch. Okay, it should be able to turn it should not pass any current, whatever the voltage is. This is for the ideal mechanical switch. But if you know, right, if you know in our power system, if you study like relay contacts and all those things, circuit breakers, like we study specifically, even if the switch is open, if there is some high voltage, what will happen? Basically, there will be a breakdown of the air. Air is between the dielectric source, right? If the dielectric is the air, right? So if some high voltage is developed, so electric field get developed and the current starts to flow from the air itself. The current starts to flow from the air itself. So obviously, in case of a practical switch, this is not possible. It cannot block infinite amount of voltage. But we are talking about ideal here. So for an ideal switch, it will be able to block any amount of voltage, infinity also, right? So again, what is the amount of power dissipated for an ideal switch? The amount of power dissipated will be again 0. Okay, because current is 0, right? That's why. Next, again, to turn off the switch, right? Turn off, again, for an ideal switch, the time taken to turn off the switch will be 0. So these are the basically characteristics of an ideal switch. So like if I want to draw the VI characteristics of an ideal switch, right? So VI characteristics, or I can say IV, of an ideal switch will look something like this. Basically, if my voltage is lying from distance to distance and current is 0, right, this is basically the x-axis. If I'm lying in the x-axis, then switch will be off. If I'm lying in the y-axis, then switch will be on, because in the y-axis the voltage is 0, but y can be any value, that is I can be anywhere, right, from minus infinity to plus infinity. So that means this is on and that means this is off. So but for practically this is not possible. Okay, but first let's do one question, right? Let's do one question on the ideal switch itself. So we haven't given a circuit and we have to draw the VI characteristics of the switch for the given below circuit. We have to draw the VI characteristics. So of this switch we have to draw the VI characteristics. So how do we draw? This is, first of all, they have told us that if nothing is mentioned, we'll assume that this is an ideal switch, right? Nothing is mentioned, this is an ideal switch, and the supply is a DC supply. This is not a AC supply. So basically what will happen is, if I keep on varying this Vs, right, what will basically happen to this switch? Like when this switch is closed, or when this ideal switch is closed, what will be the value of the current and voltage? So all these things. So how to draw? Basically, we will use two cases. So case 1, when switch is closed. Okay, so when switch is closed, sorry for that, what will happen? When switch is closed, basically the circuit will become something like this. So Vs, all these things are constant, just like like we can vary Vs, but what will be the value of the current? What will be the value of the current? So this I have to delete, and switch is closed. So if switch is closed, basically what will the value of the current? Current will be basically the Vs is constant, right? Vs is some voltage, let's say 5 volts. So value of the current maximum can flow what? Vs by R. Okay, that is the value of the current. That is the I switch, right? And what is the value of the voltage? V switch, right? Again, we know nothing is mentioned, so it is 0 volts. Now in case 2, right? In case 2, just hold on to make this smaller. Copy this case again. Just this time the switch will be open. Case 2. Switch is open. So if switch is opened, that means that no current will flow, right? No current will flow. So the drop across this will be 0. So across this the drop is 0. Okay, 0 amps current. So across this the drop is 0, and this is assumed to be ground, right? This is assumed to be common potential ground. So the whole voltage is of this Vs only. So this time, right, my I switch will be 0. Okay, I switch will be 0, but my V switch will be simply Vs. Okay, V switch will be simply Vs. So this time the V switch will be Vs and I switch will be 0. So how will you draw the like VI characteristic? So let's say this varies, right? The question framing is a bit wrong. So I will say this varies between from I can say from 0 to Vs. This varies from 0 to Vs, basically the maximum voltage. So how will the IV characteristics of my switch will look like? So this time, right, draw here I switch and V switch. So to look something like this, that during, like, it is varying from 0 to Vs. So when it is off, right, the V switch is directly equals to Vs. So it is V switch is also varying from 0 to Vs during off, and I switch is 0. So if I switch is 0, I will be on the x axis and it will go from 0 to this Vs, right? And this is off. And when this is on, right, when this is on, my Is is equals to Vs by R and my VSW is 0. So basically it is the y axis, and this will be something like this. This will be Vs by R, and this is basically on. Okay, this will be on. Okay, so basically this will be the VI characteristics of the switch. Okay, so like you can solve like this type of question can come, some basic question, anything they can ask, right? From switches they can ask any basic question, so you should be able to understand the fundamental properties of a switch. So now let's move on to the next topic, that is the timing characteristics of an ideal switch. So obviously I have told you, right, there is no like it transitions from on to off and from off to on in no time, right? In no time. Basically this is for on and this is for the off case, right? So what is happening? What is it? This is the current, right? Current. So let's say initially the switch was on. So initially if the switch is on, this is flowing, let's say some Vs by R current. Okay, Vs by R current. For the previous circuit only I'm talking about. And at this instant it instantly turned off and there is no delay. The instant it turned off, obviously the voltage got into action. So voltage, like at this point of time the voltage was 0. So this is the like waveform of the voltage VSW. Voltage was 0 when this was on, right? Voltage across idle switch will be 0, but just when this is off, right, the voltage directly is equals to Vs itself, right? Voltage is directly equals to Vs itself, so it will be Vs. Let's say for now let's assume that Vs is some constant value, let's say 5 volts. Okay, so there is no delay. Like we're plotting the current and voltage of the switch with respect to time. There is no delay, but there will be some delay, right? So basically, what is this T on? T on is the on duration, T off is the off duration, T is the switching time period. T is basically the total overall in a time period how much time the switch is on and on. Basically, this is a repeating thing, and we will use this repeating thing only. We'll turn on and off switches in a pattern. Why? We'll understand when we study about the devices. So we need this. We basically need this, and like these are the definitions. So capital T on is on duration, capital T off is off duration, T is the switching time period. Okay, for how many period this is repeating, like for until what time this is repeating, and F switch is the switching frequency, which is basically the inverse of the switching time period. And these are the notations that I will use throughout this whole chapter. Next, T switch on. T switch on is the time required to turn on, time required for the switch to turn on. T switch off is the time required to turn off. Okay, ideally, in ideal case, these are 0. Ideally, these are 0. Okay, but obviously we don't live in an ideal world, so there will be some finite time it takes a switch takes to turn on off. We'll understand that when we study about the properties of different switches, but for now we are concerned with the analysis, circuit analysis, and what happens if there is some time taken to turn on and off. We'll understand that as well. So here I have written few properties of ideal switch. You can, like, these are a few key points that I was mentioning previously. Okay, so you can quickly go through this and read all this, right? Just hold on, let me check if everything is recording. Yeah, fine. You quickly go through this and read all this, right? So whatever I have said, those are the same thing. Basically, in on state, it must have ability to carry any amount of current during on time, minus infinity to plus infinity, without any voltage drop. Voltage drop is 0. In off state, it must be able to block any amount of voltage without any current flow. Current should not flow. Whatever the voltage, it doesn't care. Okay, it will not flow any current. It is stubborn. Now, device must have 0 on resistance. So during it is on, right? It is simply short circuit. There is no resistance. So on state loss, called as conduction loss, will be 0. As 0 on state resistance, we have already proved it. So PSW is 0. So this means basically short circuit. Okay. Device must have infinity off state resistance, so off state loss called blocking loss must be 0. So if it has infinite resistance, current will be 0. So current is 0, so obviously it will have no losses. Basically, this is the open circuit. It is talking about the open circuit state. Next, switch must be able to change its state from on to off or vice versa instantaneously. Switch must be able to change its state from on to off or vice versa instantaneously. There should not be any delay. Basically, this means that my T on equals to T off equals to 0 seconds. Now, switch can be operated at any frequency. Basically, it doesn't care like what can be the T on or T off, whatever, how much smaller, like this overall conduction period, right? This can be switching time period. This can be any amount of value. This can be in milliseconds, nanoseconds. It doesn't care, because if T is in nanoseconds, obviously F switching will be very high in gigahertz, right? Gigahertz. So you understand, like whenever frequency is very high, that is very difficult. Like, what do you mean by that? Basically, I'm turning off, on, off, on, off, on. So if I do this very fast, right, this switch can get damaged. If I do this very fast, this switch can get damaged. Obviously, I may have damaged this switch now also. You know, right? If you just turn on, off and off, off and off and on, this can get damaged. So there is a limitation of this. But for the ideal switch, it doesn't have any limitation. I can turn off and off, on and off. Like ideally, I can have 0 time period as well. Okay, 0 switching time period as well, and it won't get damaged. But in practical case, obviously it will get damaged. If I just turn on and off this, okay, it will obviously get damaged, right? So we'll study about that as well for a practical switch. So basically, this last statement mathematically says that our frequency, switching frequency, can lie between 0 to infinity. Okay, it can take any values. Now let's come to the properties of a practical switch. In practical switch, right, basically like our switch will have a when it turns on, it will have a on resistance, or it can have a voltage drop as well. We'll study about the voltage drop. Okay, and during off, right, it will have a off resistance. Okay, now generally this off resistance is very high. Okay, and this on resistance is very low. Okay, so this mimics the ideal characteristics, just that it won't be exactly infinity for the off case, and it won't be exactly 0 resistance for the on case. So these two are the differences. this will be very high, but this won't be exactly infinity. Okay, so in this case, right, what will happen is obviously some current is flowing through the switch and we have some R on resistance which is very low, I do understand, but there will be some drop. What will be the drop? That will be I switch into R on. So this time my switch voltage is not 0 when it is turned on. So this time my V switch equals to I switch into R on, right? This is the voltage drop. This time my V switch is not equals to 0 as it was for the previous case. It is not equals to 0 volts. Now what about I switch? Again, I switch this time also has a limited boundation with it. It can't be from minus infinity to infinite. It is finite. What do I mean by this? Every switch has a rating, right? Obviously, through this switch, I won't be able to flow kiloamps of current. This is just a normal switch, right? Like in power systems, there are switches. Those are rated for kiloamps. But obviously, this switch also will have some rating. So, I can only flow current through this switch, which is bounded to some rating which will be given to us. Which is like in the data sheet of the switch that will be given minimum current that I shall flow and the maximum current that I shall flow. Okay, so there is a boundation in a practical switch. Now this time, what is the power dissipated across the switch when it is on? So this time, right, when it is on, the P switch, this time my V switch is not 0. So if it is not 0, obviously this time it will not be equals to 0. So even though this will be very low, right? This will be very low value. Okay. But this will be not 0. So if it is not 0, basically this is called as the conduction loss. When the switch is on, okay, this is called as the conduction loss. It has some conduction loss. Basically it is conducting but with certain loss. Okay, and obviously this time just at the instant when I turn this on, it doesn't pass current instantly. It takes some time to reach its steady state. With the timing diagram, we'll understand this better. It will take some time. I will show you. So this time, right, my T on will not be equals to 0. It will be some finite value. Okay, very low, but it will be some finite value. And it depends, right? It depends on the construction and the device as well. We'll see. Now, for the other case, I will just copy this. For the other case, what is the difference is that, just make this more smaller. Basically this is I switch will be at the top this time, which is a little bit bottom. Just hold on. This time when the switch is turned off, ideally what we want 0 amount of current. If I have turned off the switch, obviously there shouldn't, like, light shouldn't blow and all those things. But if there is some leakage current, there will be some leakage current, as even though like it is very high resistance, but there is some resistance, right? So obviously some leakage current will flow. Very high resistance I am observing, but still that is some finite resistance, so some leakage current will flow, and due to that my current, right, my current won't be 0 amps. There will be some finite current flowing through the through the switch, which is very low. I do agree, very low, but still some finite current is flowing. Okay, next, what about V switch? So again, my obviously there will be some limitation how much I can block voltages. So in reverse bias, right, when the diode is reverse bias, you have, if you are studying analog electronics, you will see that it has some rating Okay, I cannot provide it infinite amount of reverse voltage because there will be breakdown, avalanche breakdown, and the device will get damaged. So obviously there will be some minimum and maximum reverse voltage that I can give, okay, for which the diode will be working properly and it will be off and some low amount of current will flow, else there will be some breakdown and some huge amount of current will flow. We know from diode, if you have studied the diode physics, you will know. So obviously again P switching will be not 0 because I switching is not 0 and there is some finite voltage obviously, so it is not 0, and T off will also be not equals to 0. T off will also be not equals to 0, and as P switching is not 0, very low, is not 0, this will be the like you can say power loss when the switch is off, right? There is no name for it, power loss when the switch is off, and like this it has a significance, that is the conduction loss. This is the significant name for this. Okay, so these are the things about practical switches. And the VI characteristics of a practical switch, it has some area, okay, area. Basically I can give it only some maximum current, some maximum voltage, and if I'm moving in this voltage direction, this is off, and if I'm moving in this current direction, this is on, right? So if current is very low and I'm somewhere here, right, that means it is off. If current is very high and the voltage is very low, I'm in this region, right? I'm in this. So mostly what will happen, it will be something like this and something like this. The region will be something like this. Okay, so obviously I cannot lie in this region because there is some safe operating limit, okay, else this device will get damaged. So this is the safe operating area in which my VI characteristics will lie. If I am outside this safe operating area, my diode or my practical switch, like it should not be exactly diode, it can be anything, okay, that will get damaged. So this is the IV characteristics of a practical switch. Okay, so what are the timing characteristics of a practical switch? Now this is a very good thing to note here, so be pay close attention to this. So this time, right, I can observe that I switch, this is my steady state I switch current, this is my I steady state. Okay, it is not instantly reaching to that steady state value, right? It is taking some time to what it should reach to. Basically this is the, let's say this is the Vs by R current. Okay, I just turned off the switch and what do I expect? I expect like through that circuit Vs by R current to flow, but Vs by R current is not instantly flowing, it is slowly increasing, because in life, right, everything is continuous. You are continuous, everything is continuous, it is not discrete. So analog things are continuous, so it could not suddenly jump, it needs some time, that's why again when I'm closing the switch, in a practical switch the voltage will go to some low value, it is almost nearly equal to 0, so it will not instantly go to 0, it will take some time. Okay, so from Vs it takes some time to go to 0. Now this time is known as the time for the switch to turn on. When current increases and voltage decreases, this is the TSW on. This is the notation that I told you. Then for this particular duration, it is in steady state, so that switch is in on, and this is known as the capital T on. Then again I turn off the switch. If I turn off the switch, the current should go to instantly 0, right, from Vs by R to 0. But again it takes some time from Vs by R to go to 0. Here as well you can observe that the voltage should instantly go to Vs, right, according to that circuit, but it takes some time. Again in this time period, if the current is decreasing and voltage is increasing, this is known as the T switch off. Okay, time taken for the switch to take off, right. Next, this value, again it has reached steady state, so this value is Vs. Again this value is Vs again, right, and this value is Vs by R. Okay, so you can observe it is taking some time. This is the T switch off, and again this is the off period where it has reached steady state. The voltage is Vs constant and the current is almost equal to 0, or obviously it won't be exactly equal to 0 for a practical switch, but nearly I can assume that it is equal to 0. Now, so this period is called the off time. Okay, off period. Now obviously my T, right, T will be the summation of all this. So what is my switching frequency? Now my time period to turn off and on and off of the switch, a single time period, has increased. So the number of times which I can turn on and off the switch in a minute has decreased, right? Let's say previously it was taking 20 seconds to turn on and off because it was instantly getting turned on and off. Okay, I turned it on for 10 seconds and turned it off for 10 seconds. But now I want my switch to be on and off for 10 seconds, but I have to take care of these times as well, right? So let's say these take extra seconds of 2 seconds or 2.5 seconds. So to turn on, it takes 2.5 seconds extra. To turn off, it takes 2.5 seconds extra. So overall, to turn on and off my switch 10 seconds, I need to give it 25 seconds, because 2.5 seconds to turn on and 2.5 seconds to turn off. So previously I was able to do that same cycle, follow the same cycle in 20 seconds. Now it is taking me 25 seconds. I have to give it more time. Okay, so my switching frequency has reduced. So basically overall time is T on, switching switch for the switch turn on, then capital T on, the duration for which it is turning on, then T off plus capital T off, right? So these are the 4 timings that it takes for the switch to turn on and off, right? These are the things. So obviously my T has increased now. T has increased, right? So my T has increased. What can I say? So T, what is my switching frequency? My switching frequency is 1 by T. I have already explained. Now if T increases, obviously my switching frequency decreases. What does it mean? The number of times which I can, let's say in a minute, number of times which I can turn on and off the switch in a minute has reduced, or number of times for which I can turn on and off the switch in a second has reduced. So it is harmful for me. I am getting less number of turns on and off, which I don't want, right? So obviously we have to give some trade-off. So practically this will happen. We can't avoid this. Okay. So now let's understand what is the loss across the switch. So if you observe it, one thing carefully, that whenever this is reaching steady state, right, the P loss across the switch is almost negligible. Why? I have explained this here as well, right? Because it will be very low, because in this case, in the on state, the drop across it will be very low due to the R on being very low. And when it is off, right, R off is very high, so I switch is very low. So again, P switch will be it will be finite, it will be some value, it will be non-zero, but it will be very low. This will be also non-zero, but it will be 0 or very low. So I can ignore these two. What I'm interested in is in these regions, right, where the voltage and current both are very high. Okay, very high. So in this region there will be many loss. So what I will say, I will neglect the loss due to this and this. I will only compute the loss due to this and this. So over a whole cycle, what is the average power consumed by the switch? Because I have to see, right, because I am converting the power and some of the power is getting lost in the switch. So obviously I don't want that. I want all the power to reach the load. I don't want it to get lost in the switch. So I have to minimize it. So for me to minimize it, first I have to compute it. Okay. So basically, how can I compute? So the average power across the switches, average power of anything is 1 by T, taking the mean. Then integration of voltage and current. So in this case, right, in this case, this is for which time period? This is for T switch on. So this time period is for from 0 to T switch on. So T on. So this is VI dt. Now plus, again if you observe this duration, right, this voltage and current for this period when the switch is in transition to get off. Okay, other periods the loss is almost equals to 0. So loss will be almost equals to 0. T of VI dt. Okay, so this will be the basically the average power loss. Now if you want to write this thing, right, if you want to write this thing in some other way, so what you can write is this whole thing, right, this whole thing is the energy dissipated in the switch for it to turn on, and this is the energy dissipated across the switch for it to turn off. So this is simply equals to what? Equals to E on and plus E off. Okay, energy dissipated. And what we can write, these are the formulas that you should, I'm deriving, right? You don't have to remember, just know, right? This is also a formula, right? This is also a formula that can be used. So you can derive it in seconds. So 1 by T, how can I write 1 by T? 1 by T is basically the FSW, right? Switching frequency. So this will be FSW. Okay, so this is the average power across the switch. So this is the timing characteristics of a ideal switch, and these are the parameters that we have to find out. So this is what we want to minimize and all these things, right? This you should know. So what are the properties? Again, like whatever I explained in the previous like sections, all those things are written in point-wise manner. So in on state, switch has a small voltage drop across it and only can carry limited amount of current. Okay, so in on state it has a small voltage drop, okay, not equal to 0 but very small, but it can only carry a limited amount of current, right? Very low. So that is exactly what is written. Again, during off state switch has a small leakage current, so some small amount of current will flow, that will flow, and also it can only block a finite amount of voltage. It can't block infinite amount of voltage. Device has non-zero on resistance, so on state loss will be non-zero, okay, but it will be very low, but it will be non-zero. Device must have finite off resistance, so off state loss or known as the blocking loss. So I forgot this name, so this is known as the blocking loss. So I will name this as the blocking loss. Blocking loss is also not equal to 0. It is not some non-zero value. Now switches like both conduction loss and blocking loss together are taken as switching power loss, and like during it turns on and turns off, right, that is also a switch, comes under switching power loss. Switch requires a finite time and energy to change its state from on to off. As you can see, right, it requires some finite time to change its state from on to off. It is continuous, okay, that's why switch can only be operated at some finite frequency. If you observe, this is getting increased, right? Previously this can be any value, now this is getting increased as t on and t off are finite, so f switch is decreasing, so it cannot go to infinity. It has some boundation, okay. So I will say my switch frequency, basically mathematically this means my switch frequency is bounded between 0 to f switch less than f max, okay. So that is the thing. Now also there will be some energy to change its state from on to off. It will require some energy, so you can see, right, some energy is getting dissipated. Also some external circuitry is required to turn it on suddenly, right? That we'll understand later on. So during get circuit and all those things we'll understand, don't worry. So these are the few key points that you should keep in mind. So I've concised this all in a way so you won't need much time to revise all these things. Next, what are the losses in practical switch? So I've already explained the losses, right? One was the like switching loss, like this when it turns on and off, we ignored this thing, okay, we ignored this thing to derive this formula, but there can be like these losses I ignored, right? Now let's understand about these losses, the conduction loss and the voltage loss, and what are the different types of loss. So I just used one of the models, replace everything with a resistor. It can have multiple models of a switch. A switch can have multiple models. So this is the first model, that is a constant voltage drop. So if you have studied diode, you know, like we can replace the diode with a voltage drop, we can replace the diode with a resistor, also we can replace the diode with a piecewise model, piecewise linear model. So for a constant voltage drop, what will be the power loss? Okay, so the power loss, if some I switch current is flowing and like it is in on state, the power loss will be what? Basically P switch is 1 by T integration from 0 to T P of T. So P of T, what can I write? P of T equals to 1 by T, P of T equals to 1 by T integration from 0 to T V switch into I switch of T dt. So what I observe here is that my V switch, right, voltage across the switch is constant. What is the voltage? It is a constant voltage drop model, right? So it will be simply V on, the voltage drop that happens across. You can take the example of diode to turn on. So it is V on. What is my I switch? I switch, I don't know. I switch is some value, I don't know. Okay, I switch will be a function of time. Okay, I don't know. So what I can do is I can simplify this. This will be 1 by T, and as V switch is constant, I can take this outside. So if I take this outside, this will be V on integration from 0 to T I switch of T dt. Now what is this? This is basically the, if you are like want to write this in a single letter, it is the average current across the switch over a period. So this is the average current across the switch over a period. So I can write this. This will be equals to V on I switch average. Okay, so like this is the formula that you should know, or don't have to know, you can derive from here. So this is a basic formula, right? This is a basic formula that I derived. So if you just derive in second, it will take second, but if you want to remember the formula, you can remember the formula. Okay, don't remember everything in terms of formula. I will recommend remember in terms of derivations. That will be much more helpful for you. Okay, just don't remember this for a constant voltage model. Okay, this will be V on into I switch. So how many things will you remember? Just understand conceptually what is actually happening. Now type 2 model is constant resistance that I showed you earlier as well. This time, right, this time what will happen is that again everything will be same, but this time my V switch will be basically I switch into R on resistance. Okay, now my I switch again is a function of time. I switch is a function of time. So how to compute the power? So if I replace the power, right, it will be equals to basically, I will now directly do it. This will be simply I switch whole square into R on. So R on is a constant value, right? R on is a constant value. I switch is a function of time. I switch is a function of time. Okay. So if R on is a constant value and I switch is a constant of time, function of time. So what is this basically? If I take the R on outside, what is this? This is the average of I switch whole square. If you know, basically it is the IRMS whole square, right? IRMS is the mean of the, like it is the area of the I switch whole square over a time period t and root of the square root of that. So it is a square root of this thing. Okay, but we are not interested in the square root. We are interested in the square of this, because if I square this, the root will go away. So this is basically equals to what? All this I've explained in my basic network theory classes. You can go through that as well, right? So that is also a prerequisite that is required. So obviously you will come to power electronics only when you have studied network theory. So that is the most basic thing. So this is equals to IRMS whole square into R on. Okay, so this will be the formula for P switch when we replace this with a R on resistance. Okay, so again, just use the simple derivation. Don't have to remember anything. Now if you use both of this, right, this is known as the piecewise linear model, and in diodes I hope you have studied. Okay, so if you use both of this, then the drop across the V switch and I switch will be a bit difficult to compute. So basically this will be I switch will be some function of time again, and V switch I can write in terms of I switch. V switch is equals to V on plus I switch into R on, right? So basically what will happen here is that it will be combination. It will be combination of both. So V on into I switch. If I do V switch into I switch, it will be V on into I switch plus I switch whole square into R on. So basically if that happens, what will happen is this will take the first one for this V on case, V on into I switch. If I take the average of that, it will be simply V on into I average. Then for the second case, it is I average of ISW switch whole square into R on. Again, it is the IRMS whole square into R on. So that is basically what is happening, right, for the second case. So basically it is a summation of the two other powers from which we computed. So power 1, you can compute it like this. So you can derive it. Okay, you can try to derive it like it's the same derivation. I've already done the derivation, so I'm not doing it here over again. So here an interesting question came up in GATE, so we'll solve this question, and the remaining ones I will give you as homework assignment ones, and in the next lecture we'll solve all those questions. So here a MOSFET rated, this is a GATE 204 question, MOSFET rated for 15 amps carries a periodic current as shown in the figure. So it carries a periodic current as shown in the figure. The on-state resistance of MOSFET, you don't have to care about this name, right? MOSFET, we haven't studied, don't worry. If you have studied MOS physics, good. If you haven't studied MOS physics, just think of this is a switch. Just change this to switch. That's it, right? Change this to switch. MOSFET is 0.15 ohms. So the on-state resistance of a MOSFET is 0.15 ohms. The average on-state loss in the MOSFET is. So it is asking us the on-state loss. What is the on-state when it is on? What is the loss across it? So obviously here, right, it is rated for 15 amps, and we have to compute the on-state loss. So what we can do is, which model is this? This is the second model where we are replacing our MOSFET with a resistor. So basically, if I do this, when my switch is on, right, it is 0.15 0.15 ohms. Okay, so it is 0.15 ohms. So this is I switch. Okay, this is I switch, and this is the voltage across the switch. So like, what will be the answer? Basically, what is the power loss? Power loss will be again average power loss, and like during off time, right? It is it has asked us to find the average on state loss, because during off it is the current is overall zero. So during off there is no current flow, so there will be no off state loss or blocking loss. So only the on state loss will be simply the 1 by t average of the p of t. So what was it? So it is simply equals to v of t into I of t. Again, v is constant, right? V is v is the drop across this, okay, which is ISW into R on, and basically it is IRMS whole square into R on, right? IRMS whole square into R on, which we have already derived. So basically, what is IRMS? We have to find out IRMS. How to find out IRMS? So in my network theory classes, I have explained how to find out IRMS. I hope you have studied those things, right? So IRMS, right? It is the for a square one, it will be the under root of square of the mean. So basically, it will be simply area of the square. What is the area of the square? Area of the, not this square, square of this waveform. So it will be 100 square into pi. This is the area, right? Now what is the average area? Average area is the mean area is 2 pi. Then we have to take the root. So I will not go over this in more detailed manner, because this will just waste our purpose and time. So like, you can go and watch the network theory lectures where I have explained how to find this RMS, right? Of a square, of a triangular, of a sinusoid. All this I have explained. I will not waste your time. Okay. So basically, I can make you understand is that in RMS, right, what we do? We first take the square of this. Okay, square of this. The square of this waveform, right, will become what? This will be, the shape won't change because it's just a constant thing, 0 or 10. So if it is 0 or 10, this will become 100 amps, and this will be 0 only, and this is I switch. Okay, so this is 100 amps, and this is the I switch whole square. Now I have to compute the area under this and take the mean of this. So area under this is how much? 100 into pi. This is pi is the area. Then I have to take the mean. Mean is like the average, it will be divided by 2 pi, right? Overall time period is 2 pi. Then I have to take the under root of that particular thing, and exactly that is what I have done. So this will be equals to 100 square by 2, that is 50 under root. Okay, under root 50. Now what are we interested in? We are interested in the IRMS whole square. So if we are interested in the IRMS whole square, this will be P on will be 50. Basically, I'm taking the square into R on is what? R on they have given me 0.15. So it will be 7.5 watts. So this will be my answer, right? 7.5 watts. Answer option C. So this has came in gate, and this is a pretty easy question, and you will be able to solve it easily. So like, obviously for power electronics, you will need the basic knowledge of network theory as well, and obviously power electronics as well. Okay, so these are the basic knowledge, and also analog electronics. So it is better to study network, analog, and then power electronics. So core subjects you should cover at the end, not at the start. So this is the case, right? This is the case answer for this. So I have given few more questions, so you can solve it in your own, and I will solve it in the next lecture. So this is one of the questions. So now let's come to another loss, that is a switching power loss. So there was conduction loss and like offstate loss. We assume that ISW is almost 0, so we assume that it is almost negligible. But what is a switching power loss? Switching power loss is basically when the device is switching, right? I explained it. I had already computed the switching power loss. For that, it is E on plus E off into FSW. I have proved that. So we'll compute that. How to compute it for waveforms like this? It is very difficult, right? How do you compute? So basically both are changing. ISW and VSW both are changing. How do you compute? And we assume that these are linear only. We assume these are linear for our convenience. Else computing the area or the switching loss will be very complex. If we assume this as complex waveforms, it will be very complex. So this is the time, like what is how do you understand that it is going from off to on or on to off? Okay, so it is going from off to on. In this case, how do you understand? You understand that it is turning on because current is increasing and voltage is decreasing. So when the voltage decreases and current increases, so it will be off to on. So here what is happening? Current decreases and current increases and voltage decreases. Okay, so like what I can do, I can assume this has a slope, like for the current one I can assume this has a slope of m and like y intercept of c. Okay, not y intercept, sorry, x intercept. So I can put the values. So if I start from this area, if I assume this has t equals to 0, I'm starting, like my switching is starting from here, and like what happens during switching, right? Like it is basically about the transient state. So I'm going from, like, switching loss is basically the transient state loss. You can write it as transient state loss. What is happening here is that basically it is going from V switch to I switch, and what is happening is that I'm going from one steady state. I will use another color. Like this is steady state, right? It was constant here, so it is steady state. Transient, we have steady in transient. What is happening? We're going from one steady state to another steady state, and the time between that is transient. Now in this case, it is a switching period, and this is also a switching steady state, right? So I'm going from one steady state to another steady state and this steady state. So it is like reaching some value. I switch from 0 to I switch, right? So basically I can use the simple mathematical thing, functions and all those things. So my I of t is equals to, how can I compute the slope? Slope is basically dy upon dx. So how much y is it changing? It is changing I switch w, right? I switch. So it is I sw divided by dt. What is the time change? Change in time, it is t on, right? From 0 to t on. So this will be t on into t, right? In this case our x-axis is t, not x, so it will be t. And what is our y intercept, sorry, x intercept? It is 0, right? At t equals to 0, my I switch w is 0, so c will be also 0. So this is the expression for current. What is the expression for voltage? Similarly, if we compute the expression for voltage, it is going from VSW to 0. So what is the change in voltage? Minus VSW, because 0 minus VSW is minus VSW, because it is reducing. Slope will be negative, so it will be minus VSW by t on into t. And what is the y intercept this time? Sorry, what is the x intercept? X intercept is what? At t equals to capital T equals small t on, the value is 0, right? Value is 0. So if I put t on here, this is minus VSW. I have to add VSW extra so that it goes to 0. Okay, so I have to add VSW. So this time the x intercept won't be 0. So these are the two equations of my voltage and current, and if I simply multiply and do the computations, I will be able to find out my value of switching loss. So I will just do that and then I will again come back. So basically this is the expression. If you mathematically do it, right, our V of t is this and I of t is this. So if I multiply these two and then I integrate over t on period, because we are only computing the loss toward t on period from one steady state to on state, other steady state, basically the switching power loss. So if you integrate this, you will get your expression like this: VSW ISW into T1 by 6. Now again for the second case, when it is going from on to off. So when it is going from on to off, basically what will happen this time, right? My I switch will be lower. I switch is reducing, it will tend to go to 0, and V switch will increase. So I switch will become lower and V switch will become higher, right? It will block the any voltages whatever is present. So that is what will happen in the off period. So now basically what next? Like you can do the same thing, that again basically here my slope will be what? For this the slope will be M will be equals to VSW by T on, change in voltage by change in time, and same for this minus ISW by T on. So my V of t I can write V of t will be VSW by T on into T, and there will be no X intercept, okay, into T, and there will be no X intercept, and my I of t will be minus ISW by T on, and there will be X intercept of plus ISW, right? plus ISW, because at t equals to small t on, the current is 0. Okay, so now if I like do the same computation again, sorry, this will not be t on this time, sorry, this will be t off, that is my mistake. This will not be t on, this will be t off, right? So this will be t off, because it is a time taken for it to turn off, not on. So yeah, all this will be t off actually. So this, right, this will be again t off, not t on. So this will be t off, and we will integrate through t off. Okay, so this will be off here. So like this will be the value for E off, right? Energy lost for it to turn off, for the switch to turn off. And for turn on also, we have seen that it is almost the same expression. If let's say the voltage and currents are same, the magnitude of voltage and currents are same. So what is happening is overall switching loss. What is the overall switching loss? If I assume like VSW and ISW to be same almost, then it will be equal to simply E on plus E off. That is, this will be VI into T on plus T off, right? Because V and I are common, I will say V and I are almost same. This will be equals to T on plus T off, which is almost equals to like some value, right? Like let's say this is equals to T. Okay, this is equals to T. So or like this is equals to T switching also, you can say, or like whatever you want to say. Just hold on, this will be like, let's name this as T, right? Let's like write T on plus, like you can write it anything. I will write it T on plus T off, right? I will write it as only T. Okay, just for our convenience, nothing else is okay. I will what I will do is, this will be, let's say this is not T, this is okay, this is small, this is TSW. Just don't get confused with the notation. Small t is for the turn on and turn off times, and this TSW is the overall for which the switch is on and off, right? That period, like this one, timing characteristics. If we go and see, this is the overall t, right? This is the overall t. Okay, and like for on, this is T on and T off, this is the small TSW. So I hope you understand the notations here. T off, and this will be, yeah, small TSW, and this is the capital TSW, that is basically the overall time. So this will be equals to small TSW by capital TSW. This I can write as well like this power, right? Power will be average, if it is average, so over a period of on and off. So this should be the overall period, right? This is time period, this is the T capital TSW VI divided by 6 into T small TSW divided by capital TSW. Okay, so this is the power loss. This is the power loss, average power loss across the switch for a whole switching transition, right? So these formulas you can understand. I hope you can easily understand. And let's do one question. Like in gate 205, they have given one question like same figure here, right? What is happening is that my voltage is constant. Okay, in this region my current is constant and my voltage is increasing, and my in this region my voltage is constant but my current is increasing. So here what is happening? Current doesn't change, right? So voltage is increasing. So this is a switching transition. What is the transition? Overall my current is going from high to low, so it is a turn off transition, right? This is not a turn on, right? My current is going from high to low. So what I can say, my current I of t is going from zero like high to low. So this is a switching off phenomena, not a on phenomena. So turn on, these options gets cancelled, right? These options are cancelled. Now what about turn off? This is running off, that is correct, but what about the what are they asking? They are asking that the current figure shows the voltage across the power semiconductor device and current through the device during a switching transition. Is the transition a turn on transition or turn off transition? What is the energy loss during the transition? What is the energy loss? So how can I say the energy loss? So here, right, my current is constant, but my voltage is increasing. So if I just draw the waveform of power, that will be more easier for us to compute. So if I draw the waveform of power here, I will draw the waveform of power, and the area under the power will be the basically the energy, right? And what is power? Power is the V of t into I of t. So this is the power, which is the product of voltage and current. So what I am observing, this is constant. Before this, right, this is 0, right? Before this is 0. So if V of t is 0, so obviously overall the product will also be 0, and this will be some value, right? This will be some value, okay. But as this is constant, the shape will remain same. So this is triangular, and if I multiply 5 with a triangular waveform, the shape will be triangular, just the amplitude will change. So what will happen over here? This will be something like this, and the amplitude shape will remain same, but the amplitude will change. Again, just after this t1 time, right, what is happening? The current is reducing, but the voltage amplitude is fixed. So again, the shape has changed, but the amplitude is fixed, right? So this will be something like this. And what will be this value? What will be this peak value? Basically this peak value, right, will be what? It will be V times I, because at this t1 instant, right, the voltage across the switch is V and the current across the switch is I. So the peak value will be V times I, and just after that it will reduce from V times I, and just before that it was increasing from 0, right? So this will be V times I. Okay, and this period is t1 and this period is t2. Now this is a what? This is a simply triangle. I know the height of the triangle, I know the width of the triangle, so I can simply find the area, and that is what I am concerned with, right? I want to find the area so that I can compute the energy. So energy will be basically area under the triangle during the switching transition. So it is half into Vi amplitude into t1 plus t2. T1 plus t2, that is the width, right? Half into base into height. So which is this is not correct. It is Vi into t1 plus t2, and this is 1/2 Vi into t1 plus t2. So this will be option D. Option D will be our correct answer for this question. So this is a pretty easy question, and like recently also they gave one good question. You can solve this question by yourself, and like there are a few questions which I wanted to give you assignments, and in the next lecture we'll solve all those questions, right? This you can take screenshot, this also you can take screenshot, and this one also. This is the most best question, okay, of this lecture. So you try to solve this, and we'll solve this in all of this in the next lecture. Thank you for watching, and I will see you in the next lecture.